Welcome to Spring LIB.
Okay, so for a problem like this, the thing we have to remember is that the heat gained or lost by a system is going to be equal to the mass of whatever's in that system times the heat capacity of whatever's in that system, right? So if we're talking about water, it would be the mass of water and the heat capacity of water. And then it's going to be the change in temperature of that water, for example. That's true for water, right? Definitely true for water. The energy is going to be equal to the mass of the water times the heat capacity of the water times the change in temperature of the water. That's also true for solids, right? So maybe we could say Q1 is equal to M1, C1, and delta T1, where this is all about the water. Water, that's 1. Okay. But it's also true that Q2 should be equal to M2, C2, delta T2, where these are all things about the solid, our unknown material. Material. Okay, I'm going to change the subscripts here. I'm going to use W for water, because they are referring to this as material 1, and that would get really confusing. So forgive me. Bear with me for a moment here. Okay, so this first equation is all about water. Everything's sub W. Okay, and the second equation is all about material 1. Okay, material 1. Okay, now what we may recognize here is that if we combine our material and our water into the same system, they're going to come to equilibrium. They're both going to reach some final temperature, right? Because delta T is equal to, say, temperature final. That is temperature initial, right? So they're going to be tied together in that they reach the same final temperature. That's fine. But they're tied together in another way, right? Any of the heat that is gained by our material has to be gained from the water, and vice versa. If our material loses energy, the water has to end up with that energy. There's nowhere for energy to go in our system except for from water to material or from material to water. That is, we can say that Q1 is equal to QW. If our water gained heat, it was from the material. If our water lost heat, it went into the material, right? Any change in temperature that either one underwent was sort of the result of the other, right? That is to say, we can equate these two and say that the mass of the water times the heat capacity of water times the final temperature of the water, which is the same for the water and the material because it came to equilibrium, minus the temperature initial of the water, TIW, let's call it, is going to be equal to the mass of our material times the heat capacity of our material times the final temperature, which is the same for both, minus the initial temperature of our material, TI1. Okay. And this is just going to be true, right? This is just the truth of the matter. And, well, lo and behold, C1, that's exactly what we're after, right? The specific heat of our unknown material. Okay, so we should be able to just divide all these things over and we'll be left with an equation for C1. That is, I should be able to just say, okay, let's put M1 over here. Let's put, not C1. We want to leave that where it's at. Sorry. But we should say temperature final, temperature initial water. Temperature initial 1. Okay. And we'll do the same over here. Of course, M1, TF minus TI1. Okay. To end up with the expression, right? MW over M1 times temperature final minus temperature initial water over temperature final. Not supposed to be an F there. Minus temperature initial material times the heat capacity of water is equal to the heat capacity of our material.